Hello everybody, I would like to compute the Mandelbrot set in C from scratch today. And the Mandelbrot set is the structure that you see here. Probably all of you have already seen it somewhere at some point in your life. And it is defined as a mathematical set. And the definition is for a complex number C, just any complex number, for which the function f z equals z squared plus c does not diverge to infinity when iterated starting at z equals 0, for which the sequence f blah 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 remains bounded in value. Okay, so effectively that means the following. You have a function that is this one, fz equals z squared plus c, that is the function. And you pick an arbitrary complex number such as c equals, let's say, 1 plus I. That's just an arbitrary number that I want to check for whether it's part of the set. And then let's evaluate that for the first function result. So wait, f, the 0th value of z is z squared. For f equals 0, it's 0 squared here, 0 squared, plus 1 plus I, which is our c value. And then that evaluates to 1 plus I. And then and then that's the first result. And then the second result, f1 of z, and here z equals 1, z equals, in the second iteration, z equals the result of the first iteration. So here we take the first result, the result from the first computation here, 1 plus I, 1 plus I. We square that, and then we say plus c again, and c is again 1 plus I, 1 plus I. And then the result of that is 1 squared plus 2I plus I squared is minus 1 plus minus 1 plus 1 plus I. And that equals to 1 squared is 1, minus 1 is 0, plus 1 is 1. And 2I plus I is 3I, if I am not mistaken. Okay, but that is how we compute the series, and then we would take this output here at the end and plug it into the next iteration. And then the complex number c, which we checked here in the beginning, is part of the set if this sequence of numbers, if the repeated iterations of those function evaluations is bounded, then it is part of the set. Okay. Now I thought probably we can keep it very simple if we just in C compute, let's say for each number 1,000 or 100 iterations. For each complex number on the complex plane, we compute 100 or 1,000 iterations, and then we check if the value is below a certain threshold, and then we just assume it's bounded. I don't know otherwise how to check for boundedness in this case, but this would be the pragmatic engineer's approach. It's definitely wrong in some cases, but maybe in most it's not. I don't know. And if it's wrong, then we have to find a different approach to computing the boundedness. So let's create a file with Mandelbrot.c and let's include sten.io.h and let's just create a main method that prints printf hello Mandelbrot. And let's compile that. Let's compile that to Mandelbrot.c. Output file is Mandelbrot. Let's compile it and execute it. And it worked partly, but I forgot the new line at the end here. So let's recompile this. Let's recompile and execute right away. So right here I have, oops, sorry. Let me clear that for you again. So we compile and then we execute, and this gives us the hello Mandelbrot. But we can also concatenate the commands and just do the compilation and the execution right away. And this gives us hello Mandelbrot with the latest code compiled. Then we need some kind of graphics to visualize our numbers. And I'm going to use SDL2 for that, which is linked as such. And SDL2 is a graphics library that we can use to create windows. And we're going to initialize SDL first. And we're going to pass, let's see, SDL init. I always forget what the inputs are. Okay, we just pass we just pass flags. And we just need the video subsystem because we're just computing graphics. SDL video. SDL init video. SDL init video. That's it. Then we can create a window, I think. And the window takes as input SDL create window. Let me just open that for you. The window takes as input a title, X, Y, width, height, and flags. Okay. The title is Mandelbrot Set. Title, X and Y, and that is interesting here. They do accept this constant SDL window pause centered, and then the window will be centered on the screen. So let's do that. Window pause centered, and then here again, window pause centered, and width and height are going to be 900, or let's just pass constants here. And then the flags will be 0. We don't need to specify any flags. And then let's define a width of 900 and let's define a height of 600. Alrighty, let's try to compile that, and the compilation won't work because we need to add the SDL compilation flags. SDL compilation flags, let me just show you what that is. It's when you compile something in C, then you want to add this, otherwise it won't compile. Okay, it compiled, but I didn't see a window opening. And that is because we are creating a window and then the application exits right away and nothing happens. So let's just wait using a SDL delay of 3 seconds, 3000 milliseconds. And let's compile and execute. And there we have our window. Very, very good. Okay, we can delete the delay, and now let's make the window closable because, let me show you again. And let's make the delay 6 seconds. If I now execute that application, then the window is not closable because there's the delay of 6 seconds, and during those 6 seconds the SDL application won't do anything because we're delaying it. So to properly fix that, we need to have a so-called event loop that is checking whether the application is running. While the application is running, at first the application is running, so let's set it to 1, which reflects the logic value true. And then while the application is running, we're going to check for so-called events. And so let me just create a variable here, SDL event, that is an event, and we're going to fill that value using SDL poll events or poll event, and then we're passing the address of the event into that. So this would now poll the event and fill the value of the event variable. And an event is such a thing as a mouse moving over the screen, a key being typed, this scrolling wheel being used, things like that. And multiple events can happen at the same time, and that's why we do while poll event. So while that value is not null, yeah, so multiple events can be polled here, and then we have to check if the event, and now I have to look things up again, SDL event, and there a so-called SDL, an SDL event is a union of different structures. And depending on what happened, it can be anything. It can be a text editing event, it can be a window event, it can be a quit event, a controller button event, anything. But we need the event, we need the quit event. So if the event, no, wait. We have to first check the type of the event. The event type. Right, and here this structure with this pattern where while is being used when polling events is also documented here. So I'm not making this up. Right, and then we switch over the event type. Let's do that. Switch over the event type. Oops. And then what do we do? Case, case SDL mouse motion. Let's find out what other types there are. Here they are. And there should be a quit event. Yes. Okay. Case SDL quit. And if it's a quit event, we do the following. We say application running is false. And just like that, the application should be quit when we press the button. Let's see. So this is now our application window. Let's quit. And it's quitting. Very good. Oh, this makes me happy. This makes me happy. Okay, we should also add a break statement after that case. Otherwise it will fall through to any other cases we might add in the future. But let's just keep it like that. Okay, so now we have a closable graphical user interface, which is nice. And now I would like to draw a rectangle onto that screen. And we do that here. So in the loop that is running, we create an STL rectangle, rect that has a width and an X position, let's say 0, 0, a width and a height of 100. And then we draw that rectangle using the fillRect function. And what does it take as input? It takes the surface as an input that we haven't yet instantiated. Then the address of the rectangle. And then the color of the rectangle. Let's make it white. Why am I doing this? Because we will need rectangles to build the Mandelbrot set in the end. Okay, let's define color white, and white is that. And what else do I need? I need the pointer to the window surface, and the window surface is, when I start the application, it is the black part of the application window. So this is the window, and the black part that we can draw into is the so-called surface. So let's get everything that we need here. First of all, let's get the window, STL window. And that is returned from here. I hope this is correct. Unused variable, yes, okay. Let's just assume this is correct. And then we get a window surface, a so-called surface, which is also a pointer, p surface. We get that from get window surface, I think. Yeah, there it is. And we pass the p window, and that's it. And now I think the application will compile again, and we should have a rectangle on the screen. No, we don't have a rectangle on the screen. Why don't we have a rectangle? We're filling the rectangle in memory, but I forgot to use STL update window surface. Oh, there's also an update window surface rects. I don't know what the difference here is. Let's try rects. Okay, this is, okay, I see. This is for updating specific rectangular areas on the window surface, I think. So let's just do update window surface. Probably we have to pass the p window here, and then it will work. Let's see. And no, that does not work. So we define a rectangle with a width and a height of 100. We fill the rectangle here using color white. All of that should be correct. Then we update the window surface. And we pass p window. Maybe that's wrong. STL update window surface. Let's have a look. Oops. STL update window surface copies the window surface to the screen. And we pass as input a pointer to the window. That should be fine, I think. Possibly it's again some very stupid error. Let's just double check what create window returns. Create window returns a window. That's fine. Then get window surface returns the window surface. STL surface. Yeah. So what is the error? Do you see it? Let me just recompile. Of course it works, but not completely. But I forgot to add the compilation statement in the command, in the last command that was being executed. But why is it, what is that color called? Cyan. Cyan. I don't know how it's pronounced. Cyan. Pronunciation. Cyan. Okay. Cyan. Why is it cyan? Did I forget something here? Do I need another set of Fs? Yeah, okay. Now it worked. Okay. Now we have a rectangle and it's drawn on a black screen. And now we have to find out which pixels are part of the Mandelbrot set. And here, what I would like to do is, let me just copy this and open Paint. So this is the window. Let me just use that for drawing. And I would like to assume a coordinate system, for example, like this one in the center of the window. And let's say this right here is 0, 0 on the complex plane. So those are the I values and those are the real number values. I don't know how to, I forgot how to label the axis on the complex plane. And then for every pixel, let's say for this pixel, we would check this value here. Let's say this is -3. And this value here on the complex plane, and this is +1i, for example. And then we check, we feed those numbers into some method. For example, check Mandel, and we feed as input the -3, the real part, and then the complex part 1, and then that returns either true or false. So a Boolean value. I think this should work. So let's do that. Let's try to do that. We need a function that returns a Boolean value, integer in C. Check Mandelbrot. Let's do check Mandelbrot, and then it accepts an input integer. Do we use integers or doubles? Because initially I was just planning to do the pixel integer values, but if we add a zoom, I don't know if we add a zoom in this episode. If we add a zoom, we have to use doubles. But let's keep it simple and just plan for computing the Mandelbrot set itself. But we can still use make the method use doubles. I mean, it's just making it more powerful, more capable, more universal. Check Mandelbrot real, that is the real part, and then imaginary. that is a keyword, imaginary. What? I've never seen the, imaginary used as a keyword in a language. Imaginary, what is that? In C, the term imaginary refers to the imaginary part of a complex number. That is part of C? It's part of the C standard. That's interesting. But it is included with the complex.h header file. I don't know if we use a complex, if we use a library for complex numbers or if we do it just ourselves. No, let's try to use the library. Let's not be stupid, okay? Let's not be stupid. I think only if we use that library we actually learn something new. If I just hack myself into the depths of C, trying to do everything from absolute scratch and not even using a library for complex numbers, then I'm not even learning anything. Okay. But then maybe the interface of that method needs to be changed. Because here I'm passing a real number and an imaginary number, and both of those model the number or the unit on the imaginary, on the complex plane. But that might not be what we want. So there's a double underscore complex that seems to be a type. I think we have to play around with this a bit. Let me open a new file. And that is the file complex.c. No, it's not the file complex.c. That will probably conflict with the library. That is the file complextest.c. Okay? Then in complextest.c we include... No, we don't include the first part of the if statement. We include standard.io.h. Then we include complex.h. And then we will create a main method that will printf starting complex computation. By the way, I need to put my keyboard on a mat because otherwise the sounds are probably very loud for you. Oops. Then printf starting complex computation, and then we create a double underscore complex. I think it was done like that. I don't know why it's using this underscore notation, but let's just try number. We call it number, and the number is 3 plus 4 times I. Unused. Okay, it just complains that the variable is unused, and let's try to do something with it. As this text here has told us, let's just copy this and paste it just to understand what's happening here. Okay. So the cReal function, complex real, takes a number as input and computes the real part of the number, and the cImage, imaginary, takes the complex number and computes the imaginary part of that number. So let's print that out. The real part is D. and a new line. And D is the real part. And then let's do complex part. Oops, complex part. Ah, imaginary, of course, imaginary part, not complex part, because complex is the overarching term for the union of real and imaginary. Real, imaginary. Okay, let's try to execute that. We compile that file, complex.c, and the output file is, no, complex test.c. Wait, complex test.c. Oh God. I think I messed something up. Let's delete the complex.c file and let's save this to complex test.c. File exists. Yeah. Hey. Doesn't work. Let's do test complex.c. Okay. And let's also open that test complex. Okay. And then let's check the files in the directory. Test complex. Okay, so let's compile test complex to the output file test complex.c. No, of course not. And there's an issue with that. And what is the issue here? It's the formatting in the printout statements, because I am printing whole digits here, or whole integers, but this is expecting a floating point number. I think this should work, I hope, at least. Let's try again, and this worked, and let's test complex, and here, yeah, that seems to have worked. So the printout is the real part is 3 and the imaginary part is 4. Let me just add a new line here as well and retry, just so the output is looking good. Okay. So that library seems to work. Let's go over to the Mandelbrot set again and include it here as well. And then we should probably look up which functions it makes available to us. C complex.h functions. So I would like to see what do we need for the Mandelbrot set? We need multiplication and addition, basically. We need to square a complex number and we need to add a complex number. And then also we would need to have some absolute value determination to check whether our sequence of values is below a certain threshold. But that can also be done manually. I mean, by just checking the absolute values of the or some kind of norm over the real and imaginary part of the number. Okay. So give me functions. What functions are there? What is that naming? Zarkosf. Returns the complex arc cosine. Okay. Yeah, I'm quiet. I just need the product. I just need the product. Phase angle, complex arc sine, complex arc hyperbolic sine, tangent, hyperbolic tangent, complex. Where's the multiplication and addition? Am I stupid, or is this too simple to put into the library, or what's wrong? Oh, there's even a power function, it seems. Yeah, power. Or can I just use the multiplication signs in the code itself? Just a star character? Let's try. Okay, so we have a complex number. And that complex number, let's now do the following. I create another complex number. Double complex other number. And that is equal to -2 and -2 multiplied by I. That is the other number. And then we do the following. Double complex sum is equal to number plus other number. And let's then check here. Let's replace number with sum. Doesn't work. No idea. Let's do it manually then. Number, sum. Number, sum. Okay. Let's see if it can compute the number correctly. And indeed, this looks good because the real part is now 1 and the imaginary part is 2. That means that was done correctly, because here 3, this 3 plus -2 is 1, and 4 minus 2 is 2. And that is the correct result. So it seems as if we can really compute complex numbers here. That's interesting. I wonder how that works. Somehow the operands are, or the operators are overwritten, I think. But I don't care for now. I will not look further into this. I just want to have my Mandelbrot set. And the multiplication also seems to work. I can't really verify it right now. All right, that is good to know. That means we can, in our method here, start checking the Mandelbrot set. And I think the inputs are fine. We just paste double and real and imaginary values here. And then we construct, then we somehow create a C number. Yes, double complex C, that is the input for the Mandelbrot computation. And that is the real part plus I multiplied with the imaginary part. And then the next thing to do is we start the function using an integer or double, also a complex double, z, that starts with 0. And then we create a loop for, let's just do it 100 times. I have no idea how. how that's, or if that's even a good idea. Let's just do 100 iterations, performing the calculation of the sequence for the Mandelbrot set. So we need to do, the function was z equals, or is assigned, the next z value is assigned the following. It's z squared at first. Let me just pull up the Mandelbrot definition again. It's z squared plus c right here. And z squared and c are both complex numbers, so we have to create, we have to raise them to the power here, complex power. Double complex. Ah, okay. Well, we could keep it simple and do the following: z multiplied by z. That would be the power, the power 2. But we could also do c power, which raises the complex number z to the power of, and then we can put some complex number here, but that is not necessary because we just want to compute the power of 2. So we can just do this probably. Let's do that, because it's more expressive than z multiplied by z. Oh no, is it even more expressive? Not sure. Let's try to do it. I find it funny to work with a new library, so let me just try to make use of the functions available there. So c power, and then we add the number c. And then in the end we check, has the value z exceeded a limit? Or let's say is z or z exceeding a limit? And the limit, let's just arbitrarily define it up here. Define Mandel limit, and that limit is 1000. And how do I check for that exceeding? I would like to get some absolute value of that complex number. So let's say this is the coordinate system, and this is the imaginary part, this is the real part of the number. We are dealing with this number right here. The real part is this, and the imaginary part is this. And then let's just say, to check whether that value has exceeded a limit, we could technically say the R value, the real value, cannot be bigger than 1000, and the imaginary value cannot be bigger than 1000. Or we could say this vector right here, which is the distance d, cannot be bigger than something. Because if the R value is, for example, here, but the I value is still very small, then we would incorrectly assume that this is a small complex number. So I would prefer to use the distance vector here. And to do that, there's probably some function that, yeah, absolute value. I think that is it. Let's just check this here. Let's just say we have this sum. And right now the sum is resulting in the real and the value 2 plus minus 14i. That means it has a small real value but a large imaginary value, so the distance vector should be very big. I would like to find out what it is. Printf distance or absolute value, and that is a floating point number, and let's say that is ups absolute of the sum. Let's try to execute that, and it doesn't work. Why does it not work? Oh, that returns an integer, the absolute value. That's interesting. Ah, I have to use complex absolute. Of course, of course. Undefined reference to C apps. Why? That's interesting because I'm just importing complex.h. And it seems to not be defined somehow. Double absolute oops of the sum, and then we put that result here, absolute. Doesn't work. I mean, we can also write that function ourselves. I just don't get why it's not defined. Am I doing anything wrong? Please tell me in the comments if I'm doing anything wrong. Let's just try if any of the other absolute functions are available. So C apps F, not available either. And C apps L, not available. That's interesting. Then let's just create that ourselves or implement that ourselves. I will create a new method that returns a double value, and let's call it CApps. And it takes as input a double complex. By the way, just a question for you in the comments again. I'm using underscore complex all the time, but the definition here, or this documentation, says that we can also use the lowercase complex, which looks nicer, but is there any difference? What's the point of having two versions of the same thing? That would be very interesting to me to know. All right. Let's say number, and then we return. And then we have to return the square root, so we need to import math.h. Oops. Square root of the real part of the number, and that's squared. Power of that, power 2. I hope this works. Plus power C imaginary of the number to the power of 2. Just like that. And then when we compile this, by the way, this might look complex, but I think most of you have already seen it. This is just this formula. Distance equals square root of real squared plus imaginary squared in this case, or it can be anything, a plus b, doesn't matter. But you have seen this, I think. Okay, then let's compile this. I will add to the compilation, right. I will add to the compilation here. I will have to add -lm to link the math libraries, because we're using now also math.h, and that compiles. That's good. Nothing is yet happening in the graphical user interface because we have just created the computational methods here. And then we check if the C-abs, the complex absolute of the number of z or z, is bigger than our arbitrary Mandel limit. And if so, we return 0, not part of the set, and else we return 1. And we can just summarize that in one statement. We don't need an if. Return. Return, and if the absolute is smaller than the limit, then it's part of the set, which this method determines. Okay. That's good. I'm now really interested in whether that works. That's really, really interesting. So now we have to somehow in our graphical user interface, in our graphics library, we have to iterate over or loop over all the pixels and determine whether they are part of the Mandelbrot set or not. So let's do that. Let's remove the rectangle. Let me just show you what that does. It creates the black window surface again. And let's create a method, compute Mandelbrot. Compute Mandelbrot screen. So we compute the Mandelbrot set for the entire screen. Or no, let's do visualize Mandelbrot screen. And then we pass as input the P surface, because that's the surface that we're going to draw to. We're going to need it. And then let's do void. We don't need to return anything. Visualize Mandelbrot screen, SDL surface as input, P surface. And then we're going to loop over all the pixels for every pixel x. How do we do it? I think we have to do it like this. X is going to be our wait, how do we do it? So this right here is the screen. I hope you can still see it. And now in this color, this is going to be the x-axis, and this is going to be the y-axis. Yeah. Okay. I smaller than, no, x smaller than width, and then x plus plus. And then for int y equals 0, y smaller than height y plus plus. So now we are looping over the screen. I'm now wondering how we convert this coordinate system to the yellow one. that I actually wanted to use. But we'll figure this out. Let's just try it like this. I think we can probably already do something like if check Mandelbrot. We check if a pixel is part of the Mandelbrot set. Let's ignore the coordinate system. I just want to see some result. If check Mandelbrot for x and y. We probably have to make this double, or double x and y. And then, if it's part of the Mandelbrot set, then we draw a rectangle. SDL fill rectangle. And what do we fill as input? We fill a rectangle like this, and the rectangle is just a single pixel. That pixel is located at coordinate 0, x, y, of course, and has a width and a height of 1 because it's just a single pixel that we're drawing. And then we're filling the rectangle on the P surface. We provide the address of the pixel and then the color white. Color white. Great. Okay. And is that it already? No, there seems to be some error in the code. At least I get some highlighting there. Expected expression. Did I? Do I have to pass this here? Cast, I mean cast. Maybe I have to move that method down because it's not aware of the next function declaration. Let me just put it here. Let's just see if that does anything. No. No, there's a typo. Okay, there's a typo. Okay. And it does nothing. Okay. What's the issue? We fill rectangles, and then once we have visualized the screen, we get this update window surface here, which should actually do something. Let's just put it into this method here. Then we can also add a delay after the visualization. I mean, we don't need to redraw the entire Mandelbrot set every millisecond. So let's input a delay of 100 milliseconds. We can even do 1 second because we don't have any interactivity right now. No, we need to update the window surface down here because only here we have access to the window. Otherwise, I'd need to pass it into the method. Okay, I think I hear my computer doing some work, but it's not really showing on the screen. I don't know why. Visualize Mandelbrot screen. Maybe it makes sense to check if the computation is even fast enough. So let's just print this number. Let's grab those features here from the test complex code. Just like this. And let's print the real and imaginary part of Z. Let's just see. I want to see a printout that something is happening. Oh, okay, there it is. There it is. And I can't abort it. It says not a number. I think you can see it. There it is. Imaginary part, not a number. That means that something is wrong in the computation itself. It's probably some weird or some simple programming mistake. And it's probably in the cpow function, because that's the only thing that I'm not sure if it works at all. Let's just delete that and do z multiplied by z and see if that happens, if that works. No, okay, then that was not the issue, luckily. Come on, it doesn't even, the application doesn't even abort. Okay. What could we be doing wrong? The loop is starting, the nested for loop is starting at x equals 0. It's going to x smaller than width and increments, which is fine. And this one starts at y equals 0 and goes to the height of the screen. And then we're filling the rectangles here. We call the visualize Mandelbrot screen method here, which is also fine. I'm sure I've done some stupid error somewhere. Check Mandelbrot. Let's see if even the input is accepted by checking the real and imaginary part of C. Okay, let's execute. And this seems to work. Okay. This seems to work. I think one issue could be... wait, let me just abort this. Come on. Oh, God. Come on, please accept my abort. I think one issue could be that we are dealing with the pixel values, or that we feed in pixel values as input to the Mandelbrot set. However, that might not be very clever, because some of the pixel values result in really large numbers, such as pixel number x equals 500 and y equals 500. What is 500 squared? 500 squared is 250,000. And then we square that number 100 more times, which is totally stupid. I think the Mandelbrot set has to be computed on some smaller dimension. So we can't just feed in the pixel values here. We can use the pixel values to draw the pixels, but we shouldn't use as... We should somehow scale the input. Let's say we scale it by 1000. Or we scale it by width and by height. This way, the input values are always between 1 and 0. Oh God, that doesn't fix it. But now this could be due to the printouts, because the printouts are really spamming everything. But let's just again check the values of Z here. Okay, we get not a number sometimes. And also I see an infinity. Oh! Yes! There's a Mandelbrot printout. Yes! That's awesome. But let's please stop application. Oh god. So I feel successful but unsuccessful at the same time. Okay, awesome. There's our Mandelbrot set. I think you just saw it. So that was a hint of success. Yeah. Not a number, infinity. How to deal with those? C complex, not a number, infinity. I don't even know why there are not the numbers and infinity values. Let me do the following. Let me just remove the printouts here. And then I'm going to scale this by wait. Now this is basically what the coordinate system transformation does, what we're doing here. I would like to get the coordinate system right. Let's just do a constant scaling for now. And then I would like to center the x values also. I would like to offset them. So when we are on the screen, let me go here. So let's say this is the application window, okay? And then this is x and y, but in the I actually want to use this coordinate system right here, something like this. And this is my r and I. To transform x to r, I have to say x plus half the screen size. No, here the x value is 500 and the r value is 0. That means r is x minus 500. So I have to say r. Let me just create new variables here. R. And let's just also put a comment here. Transform coordinate system. R is equal to double x divided by, maybe not divided, minus the screen width divided by 2. Maybe like this. And then the result of that, is scaled by the width, or by 1000. Let's do 1000. This is basically the zoom factor. And we can do this here, zoom. We can define a new variable, a new constant. Zoom is 1000. That means that each pixel, that means 1000 pixels equal the distance 0 to 1. Okay, that is good. I think we're on a good track here. Let's do the same thing for y. For I, and I is y minus height divided by 2, and I think we also have to invert I, but let's just confirm that in paint, because here y is pointing down but I is pointing up. That's why I say, for example, this value of y is 250, but in I this is whatever, let's say 300. No, this is not so straightforward. Let me just try it like that. Let me just try it. And I will reduce this delay. Will I reduce the delay? No, let's keep it. Let's keep the delay. And there is still an error here because I forgot the semicolon at the end of the line, of course. And then we have to check Mandelbrot for R and I, the real and imaginary numbers. And just for better documentation, let's change this to real and imaginary. Real, imaginary, and done. Let's see. And there's, okay, this looks good. Looks symmetrical, and I think we have to zoom out a bit. It takes quite some time to compute this, apparently. Yeah, okay. Let's reduce the zoom level. Zoom is 500. And what else can we do to make this more efficient? I dislike a bit that this is recomputed every second, but I don't know if there's a better solution. There's probably a better solution. We could visualize the set. No, we could compute it once and then visualize it iteratively without having to recompute it every time. That would require holding the set in memory somehow, which is not too bad. It's not really hard to do. But let's just keep it like that for now. Let's see what happens. Oh, nice. Okay, that's nice. That's really nice. I find it ridiculous that my method seems to work, where we're just checking the limit of the numbers of the sequence. Now, quit, please. Okay, what can we do now? I would like to define I would like to zoom out again a bit. Well, let's say 250. And I would like to define an offset y that is, let's say 100, just to shift the coordinate system a bit. Where's our computation? I lost it. There it is. So we have to do the following. Where do I put the offset? Minus offset. It should be offset x. Offset x. Offset x. Okay, let's see. Nothing seems to be happening. I think that offset needs to be scaled as well. Probably something is being computed, but the offset needs to be part of the scaling. Of course it needs to be. Minus offset. Offset x. Whoa, awesome. Great. That's the Mandelbrot set, guys. Yeah, so I hope you enjoyed this video. I think the result is really nice. This is the Mandelbrot set. Of course, we could extend this now with zooming in and somehow generating colors depending on, I don't know how far each value has surpassed this Mandelbrot limit that we defined, which is arbitrary. I don't know, but I think this is a good starting point, and feel free to extend it, feel free to play around with it, to work with it. And that is what I wanted to achieve in this small little video. I hope you enjoyed it. Please leave a comment and leave a like and subscribe. Support me on Patreon if you want. And yeah, see you next time. I'll just let that sit for a couple of seconds for everybody to enjoy.